Okay, well, thank you for coming again, if you have been before to this series of lectures. Today I want to, the first part, deviate a little from pure astronomy. I want to talk about the so-called constants of nature, and towards the end of the lecture I will show you how using astronomy can tell you new things potentially about the constants of nature, and things with much greater precision than can be learned by using experiments in the laboratory. While I was looking through my papers, I came across this old, somewhat murky cartoon. I'll read it out to you. It says, "Look, Schmendrick, in science there are many useful invariant quantities. Planck's constant, the speed of light, Avogadro's number. Well, your salary just happens to be one of them as well." Well, some things never change, and those are the things that physicists call the constants of nature. They're really a central pillar of the study of physics, a central pillar that has a rather shaky foundation, we'll see in a moment. But what do they look like? Well, they're the things that you see in the back of the textbook of physics, of course. They're what people first of all regard as the properties of the most fundamental entities in the universe. So perhaps these are the most elementary particles of matter. So things like the masses of those most elementary particles, particles like the electron, the neutrino, even particles like the photon that we might believe to have a zero mass, that this, in a rather trivial way, would be a constant of nature. A second collection would be the strengths of the most fundamental forces of nature. In our low-energy environment, there appear to be four distinct forces of nature: gravity, the force behind radioactivity, the force behind the strong nuclear force, and electromagnetism. And these have very different strengths, and they act on quite different populations of particles. And we like to quantify and try and understand why those different forces have the different strengths that they do. But those strengths represented as pure numbers would be another part of our catalogue of constants of nature. And then the very fundamental qualities that have units like a velocity, something like the speed of light in a vacuum, Planck's constant. More subtle quantities like deviations from symmetry in nature. So if you set about trying to quantify what's the balance between matter and antimatter in the universe. So if it was exactly equal, the universe was symmetric, which it isn't, there would be a zero deviation from symmetry. In practice, there is some number which characterizes the imbalance between matter and antimatter. And all across physics, there are similar numbers which characterize the magnitude of the imbalance between, say, the right-handedness of the behavior of particle physics and the left-handedness. So the universe is not completely symmetric, right on left, that you can tell the difference between the universe viewed in a mirror and the universe not viewed in a mirror. And then there are very basic qualities that only in recent years physicists have started to regard as constants of nature. Things like the number of dimensions of space, even the number of dimensions of time. I won't say anything about the number of dimensions of space today because the next lecture in this series is solely about that topic. Well, the whole issue of constants of nature is very much bound up with units, and units very much with the Industrial Revolution. From the middle of the 19th century onwards, the Industrial Revolution brought about a huge profusion of technical and commercial and engineering requirements. People needed to quantify engineering standards, trading quantities, qualities of lubricants and materials. So there was a huge proliferation of ad hoc units to measure just about everything that was necessary in industrial processes. And it was at that time that physicists started thinking seriously about what units they should be using and whether it was advantageous to use units which were not biased by human requirements and even human dimensions. Many of the units that we use and are familiar with, so if you're over a certain age, you'll know what an inch is. An inch was originally the breadth of King David of Scotland's thumbnail in the UK. And King David of Scotland, this is about 1100, was clearly a subtle man, because in his edict he said that his definition of the inch would be the average of the width of the thumb of a small man, a middle man, and a large man. So he was conscious of the fact that different people had hands of different sizes. So this gives you an example of a unit of length which is just derived from the human body. The foot is another obvious one. The biggest one of these is the fathom, which was the distance from fingertip to fingertip with arms outstretched of your root mean square person. And it's about 6 feet. Okay. And then you get thrown in the sea. So all these units you can see are sort of unsatisfactory in a way. You have to standardize them. One man's fathom is not the same as another woman's fathom. And some of our units of time are not based on the human body, but they're based upon our environment. So the length of time characterized by the day or the year derived from the motion of the Earth, its spin on its axis or its orbit around the Sun. Again, for many practical purposes, those measures of time are constant enough. But if you're doing very high precision work, they're not really very good, because the Earth's spin is changing with time, the Earth's orbit around the Sun is also decaying, and those units of time are steadily ebbing away and changing. In about 1870, Lord Rayleigh and James Clerk Maxwell first proposed that standards of mass and length and time ought to be based on properties of what we now call atoms, what Maxwell always called molecules, and on constants of nature. That if we set our units on these non-anthropomorphic standards, which were believed never to change, then this would be a sure and secure foundation for the measurement of time and for the definition of length. Much better to define length by some number of wavelengths of light emitted by a sodium atom than to refer it to the size of some rod sitting in Paris or London or Washington, which will have molecules evaporating from its surface and will change as the temperature and the environment alters. So today, for example, in the measurement of time, we've moved, therefore, from these rather anthropomorphic planetary units to measuring time in terms of the period of oscillation of fundamental atoms. And those units of time are defined in terms of those constants of nature which determine atomic structure. Now, during this business in the 1870s of trying to come to grips with units and standards, there was a rather remarkable Irish physicist, George Johnson Stoney, who ended his career actually not too far from here. He retired to Hornsey. And he was a remarkable astronomer and instrument builder. He was the first person that realized that you could deduce whether planets had atmospheres or not by working out the escape velocity from their surface. And so you could show that the moon could not hang on to an atmosphere even if you put it on its surface. And he was commissioned by the British Association to come up with some rationalization of all these engineering and commercial units for the meeting of the British Association in 1870. And what he did surprised everybody. Johnson Stoney had many other strings to his bow. What he's famous for in physics was that he predicted the existence of the electron. He invented the name, the electron, and he predicted what its charge would be. He was obviously somewhat obsessed with the electron. He was Turing's uncle, Alan Turing's uncle, and in his memoirs that his mother recorded, Turing says they always remember going to Uncle Stoney's sort of for Christmas and for Easter, and all the children used to call him Uncle Electron or Electron. So you get the idea. Well, what Stoney did was to say, well, I want to sweep away all these human units, and we're going to focus on what we might call absolute or natural units. And this he managed to do using the charge on the electron, the gravitation constant of Newton, and the speed of light. And the same thing was done a few years later by the famous German physicist Max Planck. And these units nowadays are actually known as Planck's units, although they were really first invented by Stoney. So the idea is to take three of the fundamental constants of nature, say Newton's gravitation constant, which tells you how strong gravity is, Planck's constant, which tells you how the quantization of energy is done in nature, and the speed of light. Stoney used the charge on the electron instead of Planck's constant, which wasn't known until the end of the 1890s. And what you can do with those three units of nature is manipulate them in such a way that you can form quantities which have units of length, of time, and of mass in one and only one way. So if you came to the first lecture, you'll remember that we've encountered this Planck length. So notice how it's formed. You take the square root of g times h over c cubed. All these quantities have various units of length and mass and time. Speed of light, of course, is length per unit time. It's a speed. And if you combine them this way, you get a quantity with units of length. If we express it in our units, it's fantastically small, 10 to the minus 33 of a centimetre. And that shows you, in some sense, the mismatch between the natural length scale on which the laws of physics and the universe thinks, if you like, and the units that we've chosen for our convenience for measuring the size of sugar lumps. Similarly with time, this unit is just this one divided by the speed of light, 10 to the minus 43 of a second. So this is the tick of the fundamental clock of nature. Fantastically small. Our universe is 10 to the 60 of those Planck times in age. The Planck mass is not so bizarre. A few times 10 to the minus 5 of a gram, about the mass of the average fly's leg, as you probably know. But if it's converted to an energy using E equals mc squared, it's fantastically high. 10 to the 19 times the energy of a single proton. So this is 10 to the 16 times higher energy than our most powerful accelerators can achieve. So it really is extreme when you look at it that way. So these are standards of mass, length, and time which are not tied to any human artifacts. They're reflections of the gravitational, quantum mechanical, and relativistic character of the universe. I'll show you a transparency that I showed in my very first lecture. If you didn't come to that, it might help you to envisage how small that Planck length really was. What I told you then was if you took a sheet of A4 paper, I reminded you that if you tried to fold this in half, you wouldn't be able to fold it in half more than 7 times. If you can, I'll give you £1. If you can't, you give me £1. But if I could fold it in half 30 times, cut it in half 30 times with my laser cutter, we'd be down to the size of a single atom, 10 to the minus 8 of a centimetre. Keep going, another 17 foldings, we're down to 10 to the minus 13 of a centimetre, the size of a single proton, the nucleus of the hydrogen atom. If you could cut it in half 114 times, it's a lot, but it's not unimaginable, then you would be down to this Planck length. And that's the scale on which, in modern physics, the very nature of space and of time become uncertain, and we have no theories that can tell us the nature of space and time on that scale. So doubling moves very fast, and the Planck length doesn't seem to be very far away when you think about it like that. Okay, well, these quantities still have units, of course. So the Planck length, as I've expressed it, 10 to the minus 33 of a centimetre. The key that physicists really are focused upon to unlock what's going on here is to say, well, we don't want to think about constants with units, because if we were to ask a question like, is this constant really constant, then how do you know that the measuring ruler or the unit which you're using to measure it isn't changing? So you want to express constants in a way which renders them dimensionless, so they're pure numbers. How do you do that? Well, suppose you have the mass of the electron. Let's divide it by the mass of a proton. The result has no units at all. So we take the constants that we have, even if we express them in So we have something that's a length, we divide it by a Planck length. So we have things that are pure numbers. So here are some examples, some famous examples. Something called the fine structure constant, the most famous constant of nature. It's known to very great precision, very large number of decimal places, measured by the quantum Hall effect. Roughly, its value is 1 divided by 137. It's made out of the charge on the electron, Johnson-Stoney's electron. Planck's constant divided by 2 pi, that's what the little bar means, and the speed of light. So it's a pure number. This is the combination of E, H, and C, which has no units. So if you want to measure E in any units you choose, similarly, use the same units for H and C, you'll always get this 1 over 137. 137, ubiquitous number in physics. No, it's the number that's going to open the little locks on every physicist's briefcase around the world. You'll be able to get into their ATM accounts using this number. If that fails or you need 4 digits, you should try the next number, which is 1836. Wolfgang Pauli, who was a great physicist who predicted the existence of the neutrino and much else in modern physics, who also had a rather mystical side to him. He was a patient of Jung's for a long time, and they wrote a book together about synchronicity. And Pauli, in his final illness, was really rather spooked when he entered the hospital in Vienna. He found he was given room number 137. So here's the second of these ratios, the ratio of the proton to the electron mass. And last one that looks a bit like this. It's the sort of gravitational version of the fine structure constant, big G times the mass of the proton squared over this combination. And this is a fantastically tiny number, 10 to the minus 39 roughly. So this is a reflection of how weak gravity really is compared with electromagnetism. So these are some of the mysterious numbers that physicists would love to explain. And one of the great scandals of physics, which you never hear about, is that although experimentalists have measured these numbers to ever greater precision, and it's one of the sort of key activities of a certain area of physics to measure these standards to great precision, no one has ever predicted the value of any of these dimensionless constants ahead of time. Nobody has the foggiest idea why any of these numbers are exactly as they are. And this would be a great triumph of any truly fundamental theory. It should be able to tell us why these numbers take the values they do, and whether they could be different. So there are all sorts of questions of this sort that we could pose. So we might ask whether some future or even present theory of everything, like string theory, might be able to predict some or even all of these dimensionless constants. Well, some while ago, when people first had the idea of theories of everything, people were quite confident that such a theory would uniquely and completely explain these dimensionless numbers. And the universe would be shown to have really only one possible way in which it could be. There was only one consistent universe. As people have started to explore the candidates for such theories, I think that confidence has ebbed away. It will no doubt be that many of the constants of nature will be determined in these theories, but a huge number of them are not. That it appears, perhaps in some cases, that they're determined almost at random. So they're determined by processes rather like this pointer suddenly falling in one direction or another. There's a symmetrical situation. If we let go of the pointer, it becomes asymmetrical, and a particular direction is picked out. It's rather like picking out a value for a constant. So I think now physicists do not expect that a theory of everything will tell you everything, even in the sense of the numbers of physics. Simple questions you could have in the back of your mind. How many of these constants are there? And how many of them are going to be left free and unspecified in this way? Some of these are not new questions. Einstein worried very much about these type of questions and about constants, and he made this famous remark that he was interested in whether God could have made the world in a different way. And what he meant by that, he was thinking about constants. He wanted to know whether the ultimate theory of everything, as we would now call it, would have any free constants in it at all. He didn't believe it should. So he thought that the fundamental theory of everything would leave nothing free. So he didn't think at that time that there could be a situation where some things fell out at random. But that was a long time ago. So he wondered then whether the world could be made in a completely different way, with different choices of the constants. One way of thinking about this, and so this is the sort of thing you think about if you come on the train from Cambridge to London, like today, that the most interesting thing to see on the journey from Cambridge to London are the electricity pylons that sort of pop up every now and again. And there's an interesting thing to notice about electricity pylons, and that is that they're all made by lots of little triangles. So the basic structural unit is always a triangle, and then sometimes there's another triangle inside a triangle, and so on. Now there's a reason for that. That triangles are rigid. So that is, if you take a triangle, make a triangular metal framework, and then you try to shift it, you can't. So it's rigid, it doesn't distort. If you have a parallelogram or a square lattice, then of course if you wobble it, it shifts into a parallelogram. It sort of distorts. So that's why you don't make your pylons out of, or structures out of these shapes, because they can bend and shift and shear. So we're really asking whether the universe is rather like the triangle. That is, that given the constants of nature, is it absolutely rigid? So you can't change it a little bit into another universe where the constants are just very slightly different. Or is it like the parallelogram, where you can sort of slide it sideways, and there's another universe waiting that holds together okay, but with slightly different values of the constants? Well, here's a little sort of rhyming slide. I'm sorry there's not 7 of these. I mean, I think in the sort of ecclesiastical tradition there ought to be 7 of these, and they all ought to begin with P, but I can't do that. So progress in physics, seems to me, revolves around doing things with constants on many occasions. So the first of these types of progress I characterize as revelation. So the idea that you discover that something that you hadn't realized was a constant of nature does seem to be one. The second type of progress occurs when you elevate the status of something that previously you thought was just a quantity describing something locally, something like the speed of light. Along comes the theory of relativity, and the status of the speed of light is elevated into something much more fundamental in our understanding of the universe. Sometimes one progresses by a process of reduction. That is, that you discover that you have perhaps a list of 2 or 3 constants of nature that you thought were all separate and distinct. But you find that there's a hidden formula that links them together, so that you can reduce one of them to some other ones. So the permeability of free space and the permittivity of free space, you multiply them together, lo and behold, 1 over the speed of light squared. A fourth thing I call here elucidation. This is really when you discover that some quantity, some physical quantity like a temperature or a time that you measure or you predict in nature turns out to be determined by an unusual combination of fundamental constants. A very nice example is Stephen Hawking's prediction that black holes are really black bodies, that particles can escape and are radiated away, and the black hole has a temperature. And when you compute that temperature, it depends on g, the gravitation constant, c, the relativistic constant, the speed of light, Planck's constant h, Boltzmann's constant k, which is a thermal constant, as well as the mass of the black hole. So you immediately have elucidated the fact that black hole evaporation is a gravitational, a thermal, a relativistic, and a quantum effect, which is rather remarkable. The last 2, variation, rather dramatic if you discover that something you've always believed as a constant is really a variable. And finally, something we've never managed to do, whether you can predict, enumerate, determine the value of some constant of nature. This might turn out to be the acid test of some future theory of everything. Well, when you think about constants of nature, you think about numbers, and when you think about numbers, you think about numerology, and when you think about numerology, you think about Miss Marple. Right? So why you think about Miss Marple is because coincidences occur between numerical values of quantities. And as Miss Marple pointed out, coincidences are always worth noticing. You can always throw them away later on if they're only coincidences, but they might be an important clue to some unknown mathematical formula. Well, some things are really pure coincidences. Here's an example, which I worked out. So I confidently assert that this has no physical significance whatsoever. It's not a patentable result. On the other hand, if it does turn out to be, you heard it here first. So there are coincidences which I regard as pure numerical coincidences, and people often write to me with those. But there are other coincidences that have an interesting history in the subject of cosmology and astronomy. And they began with the famous name of Paul Dirac, one of the great inventors of quantum mechanics, the person who predicted the existence of antimatter, and much, much else besides. So the greatest British physicist since Newton. Well, what Dirac did, curiously, in 1937, it was just when he was on his honeymoon, actually. So he did his calculation on his honeymoon, and he actually wrote a letter to nature about it. In those days, a letter to nature really was a letter to nature, and it was published just a few days after it was received by the editor. So on his honeymoon, Dirac wrote this letter to the editor. Later on, Gamow remarked to Bohr when he read this paper, "Look what happens to people when they get married." But there are many Dirac stories you probably know, and there is one about his wife that I learnt from my supervisor, Dennis Sharma, who was a student of Dirac's. It seemed that each Sunday afternoon, Dirac, I think it must have been something of an ordeal for such a reticent person, used to entertain members of the physics group in Cambridge to tea at his house, and they would go each week, and Dirac would serve some cakes and so on. And they went one Sunday, and there was a relatively young girl serving tea and cakes, and somebody asked him, "Paul, who is that young girl?" And he said, "Oh, that's Wigner's sister." In fact, it was his wife. They'd got married the previous day. Well, what Dirac noticed was that if you asked how many atoms are there in the visible universe today, so the visible universe has a radius equal to the speed of light times the age of the universe today. So there's a formula for this. Don't worry about the details if you don't know it. You just work out the density of the universe, multiply by its volume, divide by the mass of an atom, mass of the nucleon, and you've got the number of particles. And today it's an enormous number, 10 to the 78. Very strange. And then he worked out another large number. It's the ratio of two which we looked at just now. Take a proton and an electron, or rather take two protons, and ask what's the ratio of the electric force of repulsion between them and the gravitational force of attraction. And it's E squared, the charge in the electron squared, divided by gm squared. Put the numbers in, it's 10 to the 39. So electromagnetism is 10 to the 39 times stronger than gravity down on the scale of atoms. Well, these are not only weirdly large numbers, but weirder still, this one seems to be the square of this one. So what Dirac said, well, look, it can't be a coincidence that there's this simple relationship between these numbers. There must be a hidden relationship that we don't know, that n really is roughly the square of n1 squared. And this is sometimes called the large numbers hypothesis. It's a very radical thing to propose, because this object has just got constants of nature in it. This has got constants, but it's also got the present age of the universe. So if this number had been worked out 1 billion years ago, or 1 billion years in the future, there would be a different answer. Each day the visible universe gets a little bigger by one light day, and this number goes up. So if you put n equal to n1 squared, one of the traditional constants of nature has to become a time-dependent thing. Well, Dirac had been working very hard on things like C, M, E, and so on for his theories of atomic structure, so he wasn't going to mess around with those. So he proposed that big G fell inversely like 1 over the age of the universe. So it's first prediction that there should be a time variation of one of the constants of nature. This idea didn't last very long. It was very easy to show that this had bad consequences in our geological history. All the oceans on Earth would be boiling in the Cambrian era, and we wouldn't be here. But where it led in 1961 was a much more interesting insight. It turns out that if you take this relation of Dirac's, that n is the square of n1, it is exactly the same as the statement that T is roughly equal to the age of a main sequence hydrogen-burning star, like the Sun. And what that is saying is that the time that we live in the universe is roughly equal to the time it takes for a star to settle down and burn hydrogen. And that is not surprising. We couldn't exist at a time much, much less than the time required for stars to form and burn stably. We would not expect to be here also when this time was much bigger than the time it takes for stars to burn hydrogen. So this very strange coincidence that this number is the square of this one is just the statement that we live at the sort of time in the universe when stars are around and form stable environments. And that's not a surprise. We wouldn't expect to exist in a universe where this was not equal roughly to the square of this. So what this did was to introduce into the subject the recognition that some of these things that look like coincidences are really consequences of the fact that our own existence is part of the story. Well, this recognition that there was a connection between the constants of nature and the conditions needed for life to evolve in the universe and persist led people to think of what would happen if you tried to change the constants of nature. And in many, many cases, if you make a little change, say in 1 over 137 or various other constants of nature, you discover that unfortunately you have no atoms, or you have no complexity, you have no life, no astronomers, not even any Gresham professors. So it's a very bad scenario indeed. So here's a little picture. Back here. So what's done on this picture? So here's our number previously. This would be 1 over 1,836, the ratio of the electron to proton mass. And here's our 1 over 137 number. And we are here, as they say on the underground. There's always that alarming notice that service is normal. So we live sort of here, just at this little point. And then you can play a little thought experiment and say, well, what will happen if the world were changed and you were to change these numbers? And bad things happen in many cases. If you move up into this purple regime, there are no ordered structures. So you can't, in atomic physics, have situations where there is very well-defined order, the sort that you need in DNA for replication, or in solids or materials. Over here, there are no non-relativistic atoms at all. And up in this yellow band, there are no stars. So a star is just a big lump of stuff, big enough so that the pressure of the stuff at the center is great enough to raise the temperature to start nuclear reactions. So Jupiter wasn't quite big enough, it stayed as a planet. In the case of the Sun, it was big enough. Pressures were great enough at the center, nuclear reactions began and persisted. If you stray outside these little railway lines here, these very thin ones, it turns out that protons, which you and I are largely composed, will all decay before the stars ever form. So we really do live in a rather straitjacketed situation, that if you wander away outside of those lines or up into the coloured regimes, then the world is completely different and literally unimaginably different. Well, one of the things that one might then ask is, well, let's suppose we approach this unusual situation that we do live in a universe that seems to fit rather nicely into that very narrow region which allows life to develop and exist. If we strayed out of it, that wouldn't be the case. One reaction to this is to imagine that in some sense all possible values, or a very large number of possible values, of the constants of nature actually exist. Now, you can think of this in two ways. If our universe is infinite or just very large, then the constants might vary from place to place in the universe. We saw in the last lecture how the inflationary universe predicts that such a thing should occur. And in that case, you could have regions of the universe where the constants fall out in a way that supports life, and other regions where it doesn't. Or you could be more metaphysical and imagine that there are other parallel universes, in some sense, fully fledged other universes with different permutations of the constants of nature, and in some of those universes things fall out to allow life to exist, and in others they don't, and not surprisingly we live in one of the ones where it's fallen out all right, just as you recognise the coincidence that you happen to be listening to a lecture at the moment, I happen to be giving one. Just to recap from the last lecture, you remember one of the messages of the inflationary universe. This shows us how our whole visible universe today is the rapidly expanded image of a tiny quantum fluctuation early on. But if we could see beyond our visible horizon today, we would see conditions that were arrived at from the expanded image of other quantum fluctuations. And so we predict in this scenario that if you went far enough beyond our horizon, you would find things becoming very different to what they are within our visible horizon. And that difference even extends in these theories to values of some of the constants of nature, and even the number of dimensions of space. Well, so much for the sort of chaotic inflationary universe motivation. This picture then starts to make you think about something else. Why should constants be constant? Okay, why do we stick so rigorously to this idea that constants are constant? There are various reasons why at present, in the last few years, that there's been enormous interest in exploring the possibility that some constants are not constant at all. The reason why this is suddenly not quite so radical as you might imagine is that the candidates for fundamental theories of everything, string theory, M theory, of which you will have heard, have a very unusual feature. They predict that the world has more dimensions than the 3 that we walk around in. In the case of string theory, 7 extra dimensions, M theory, 1 more. And one of the things that means is that the true constants of nature are not defined in our 3 dimensions. They're defined in the total number of dimensions. And in these theories, it's imagined that 3 of the dimensions have become very large and we walk around in them. The other dimensions are fantastically and imperceptibly small. So you see that the constants of nature that we measure in 3 dimensions are like the shadows in 3 dimensions cast by the true constants in 10 dimensions. And it is quite possible for the constants in our 3 dimensions to change, whilst the truly fundamental ones in 10 dimensions don't. So by making our constants change, you don't destroy anything about the fundamental laws of nature. In fact, exploring as to why constants vary or not, whether they vary, gives you a way of probing these extra dimensions. In these theories, if there are 7 additional dimensions of space, and they were to suddenly start to change very slowly, then we would see that immediately. Our constants of nature would change at the same rate. So you could regard little variations in the constants as manifestations of little changes in these other dimensions. Also, we know that some of the constants of nature arise through processes, as I illustrated just by dropping this pointer, through what physicists call symmetry breaking. So a sudden, random breaking of a symmetry. So something falls out in one place differently to what it falls out in another place. So just like having a bar of iron, we heat it to very high temperature, above 750 degrees, then it's not magnetized. The atomic orientations within it are all random, and it's a completely symmetrical situation. As it cools below the Curie point, 750 degrees, suddenly the symmetry breaks, and it will either end up with a north pole at this end and a south pole at that end as a magnet, or with equal probability, it might be the other way round, the north pole here, the south pole here. So if you had thousands of these bars, which you cooled down in different places, you would find that roughly half of them would have north-south orientation and the other half would have the other orientation. So these symmetry breaking processes can lead to variations in constants. A given constant might, in a fundamental theory, have a piece which is absolutely fixed by the laws of nature. It's the same everywhere, never changes. But as a result of this process, it has another addition, a part that's random, maybe a small addition, it may be a large addition. The last motivation, though, for thinking about varying constants is you really should test all your assumptions in science, probe as accurately as you can this assumption that constants of nature are really constant. Well, over the last 4 years or so, I and various collaborators in Australia and the United States have been pursuing an observation theoretical program which was designed to probe the constancy of one of the constants we introduced earlier. And that is the so-called fine structure constant, this combination of E and H and C, 1 over 137 number. And this controls all atomic physics. The sizes of atoms, the densities of materials, spectral lines, and so on. What sort of laboratory limits do we have on whether this is constant or not? Well, using atomic clocks, which are now fabulously accurate. So your atomic clock on your wrist is now accurate to 1 second in 50 million years. So it's fairly good. To give you an idea of progress, Harrison, you remember of longitude fame, his best clock H4, 1716, this was accurate to 39 seconds over 47 days. Pretty remarkable at that time. But look at the fantastic gain by using essentially atomic physics, constants of nature. So by monitoring the stability of atomic systems using atomic clocks, the rate of change of the fine structure constant, if there is a change, divided by its value, is less than 15.4 times 10 to the minus 16 per year. So in the whole age of the universe, 13.7 billion years, it's changed by less than 21 parts in a million. Well, this sounds very high quality result, but we realized early on that we could do a lot better than this by using astronomy. And the reason you can do that is because light comes to us from objects at the edge of the universe, like quasars, and that light takes perhaps 10 billion years to reach us. And if we ask the right questions about the light, we can make a comparison between the atomic physics that produce the light and the atomic physics here in the laboratory and see if the two are the same. Well, the objects that one wants to use to do this are quasars. These are astronomical objects discovered in the 1960s. They're about the size of a solar system, it appears, but they give out 100 billion times more light and energy than a solar system. They give out the amount of energy of an entire galaxy. And this means you can see them far away. And they have a nice wide collection of absorption lines and emission features across the whole electromagnetic spectrum. So there's lots to see. So here is a typical spectrum. What we're picturing here is a quasar, here is us. It emits light towards us, which will pass through clouds of dust and gas close to the quasar on the way. And its light will be absorbed by those clouds. And when it is, in the spectrum, you will see characteristic features of particular elements in the dust clouds in between. And what we sought to do was to focus on a particular aspect of these spectra. These were the lines which are significantly affected by relativistic correction. So there's a reason to do this. You get big sensitivity gain. And we set about comparing in each of these spectra the separations between two absorption lines, say between iron and magnesium, iron and lithium, and so on. And to compare those separations in the spectrum of the quasar with measured values in the laboratory. At first we had a problem because we could measure them with instruments like the Keck telescope more accurately than anyone could measure these lines in a laboratory. But gradually, people on Earth caught up. Previously, they hadn't had a motivation to measure spectral lines to that sort of accuracy. And what you end up with is really a characteristic signature of a quasar. In terms of these separations, here's a little picture here, it's a little busy. We're looking at all different absorption energy levels here. And here's imagining, suppose we make a shift in the fine structure constant. This is making it smaller at the quasar than it is in the laboratory, in some units. And this is the wavelength of the light that's emitted by these elements. So you can see what the effect is. There are some species, like silicon, where if you shift the fine structure constant, it doesn't really have very much effect. And then there are others, if you change the value, you create very large effects. And what's interesting is in some elements, the effect goes in that direction, it goes to increasing the wavelength, and for others it goes in the opposite direction. So if you were to compare silicon with all the others, and iron with all the others, you produce a massive directory of fingerprints which correspond to what would you see if the fine structure constant was smaller at the quasar than in the laboratory. So this was done for a huge amount of data, looking at 140 quasars, 950 spectra, all taken by 4 or 5 different observers using different instruments. And the end result of this analysis was really rather dramatic. And ever since has been creating a huge amount of interest in the world of astronomy. There's about 1 paper posted on this problem on the electronic archives every day. Generally theoretical papers, observational papers take a much longer time to generate. So what's being shown here is the inferred shift in the value of the fine structure constant compared to its value here and now. When we look at objects that are 11 billion years back in time, 10 billion years back in time, and so on and so on, if there was no shift, the data would go along the zero line. Each of these points here contains about 12 quasars worth of data. If we separated them all, the picture would be overwhelmingly full. And what you see here is that there is a persistent, statistician's language, 6 sigma statistical effect. So there's absolutely no doubt here that there is a statistical effect. Statistical significance is a strange thing. If you look in the social sciences, 2 sigma, 3 sigma is thought to be overwhelming evidence, even in medicine. No particle physicist would even look twice at a 3 sigma result. So 5 sigmas required to discover an elementary particle at CERN. And LET was turned off because it could only get 4 sigma evidence for the Higgs. So it's a strange difference of culture. But this is, so statistically, an overwhelming result. The question is, what's the cause of it, not whether it exists. So is there some bias, some of the fine structure constant? I'm going to have another microphone, I think. And if you like a single number, the final story from all the objects is that one has a shift of a few parts in a million in the value of the fine structure constant from the quasars 10 billion light years away to the present. And this is really tiny. This is an effect that's many, many times smaller than the accuracy of that very best laboratory experiment. Nothing changes in in laboratory physics because of a change in the fine structure constant at this level. Okay? Its smallness is a reflection of the fantastic sensitivity of modern telescopes. Well, the last thing to say is suppose one starts to build theories of variations of the fine structure constant. Jaume Gresham and I, with Harvard Sandvik, produced a generalization of Einstein's theory of general relativity, which includes the variation of the fine structure constant. This is fairly straightforward to do, because if you start changing something in the laws of physics, then the changes are quite constrained. They have to conserve energy and momentum, and they gravitate. And it turns out there really is just one way to do this, and to work out such a theory. It's got only one free parameter in it, which is, in some sense, the magnitude, the strength of the variation. And you can fix that one free parameter from the data, just as you would fix the value of any constant of nature. What does this theory predict? Well, its predictions are rather curious, rather unexpected. So it predicts that if alpha can vary, then in the first 50 or so thousand years of the history of the universe, that we called the radiation era, when the universe is too hot for there to be atoms, there's no perceptible variation at all that actually occurs. After that, the fine structure constant increases very, very slowly, just logarithmically in time. And this prediction of an increase is, of course, what's being seen in these observations. Alpha is smaller in the past, larger today. But then the last little detail of the predictions is that we saw in the first lecture, astronomers have discovered that in the last 4 or 5 billion years, the universe's expansion started to accelerate for reasons that are easy to describe, but fundamentally difficult to understand. And it turns out that once the universe does start to accelerate, this type of variation, and indeed that of any other constant you try to vary, turns off. So the epoch during which there actually is a variation is really quite small. And this type of prediction fits rather nicely with these observations for what it's worth, that you don't get such dramatic consequences as you might have imagined, that a slow logarithmic increase of the fine structure constant allows the value when the microwave background is last scattered to us, when elements are made in the early universe, to be so close to the present value that there's no real difference. So you notice that there's a tantalizing hint here. We don't know why the universe is accelerating, but suppose that it wasn't, and you were to take a long-range look at cosmic history, then what would happen was the fine structure constant would just keep on increasing and increasing and increasing. And eventually there would be no atoms, no stars. So all complexity would ultimately disappear. And in some mysterious way, the onset of acceleration in the universe stops those changes, allows atoms to persist, allows life to exist in principle into the future. The great mystery and complication about these observations and theory is that it's all very well having predictions about what happens out on the scale of quasars, and you might be tempted to compare those observations with measurements in the laboratory or deductions from deep within the Earth about whether the fine structure constant could have changed in geological history. But the situation in the Earth and on the laboratory is rather different. And you mustn't compare with quasars unthinkingly. Quasars taking part in the expansion of the universe, whereas the material that settled down to form the Earth and eventually forms our laboratories is not expanding with the universe. It's undergone a rather complicated history and is now stationary in some way. So there's a difficult astrophysical problem of trying to predict what we should see here and now in the solar system if we see a variation on cosmological scales, extragalactic scales. And roughly speaking, we should expect to see a much slower variation, 100 times slower, in our local environment to what we should see far away. Well, lastly, one last exciting prediction of all this. What you really want is a different sort of experiment to see whether your first experiment is biased or not. Famous experiment we all know, Galileo's dropping a feather, as it were, or a ball bearing and a big rock from the top of a high tower, I don't think he ever did this, or if he ever did it, he certainly didn't see what he claimed. This experiment, you remember, was done by the first astronauts who landed on the moon. So they really did drop a feather and a rock. The moon is a pretty good vacuum, and they did hit the ground at the same speed. So this is known as the principle of equivalence, or the principle of weak equivalence, that all masses fall with the same acceleration in a gravitational field in vacuum. Now, that's the case in a world where the fine structure constant doesn't change. Now, remarkably, if the fine structure constant changes in time and in space, whatever your theory is, this is no longer true. The variation of the fine structure constant means there's a sort of field of force in the universe that grabs onto the ingredients of the fine structure constant, particularly electric charge. And if you have something that's made out of a feather, then there are fewer charged protons in its nuclei than in the charged protons of a lump of iron. And so these two materials feel that force field differently, and they fall differently under gravity, and they hit the ground at different times. Now, if the quasar data is correct, we can predict what should be the ratio of the difference in these accelerations over their sum, and it's about 10 to the minus 13, fantastically small. The best experimental limits we have at the moment just say that this quantity is less than 10 minus 12. Not very far away. But you really can't get that extra factor of 10 on Earth. There's a reason why it's 10 minus 12, just to do with the terrestrial environment, the atmosphere and so on. But by going into space, there are projects planned like STEP in the next 4 or 5 years, which will reach, supposedly, a sensitivity of 10 minus 18 here. So even if they do 100 times worse than they claim, they're exaggerating, one should easily encompass this number. And so it's a very exciting prospect that by carrying out a space experiment, watching things falling in space in what's in effect a perfect vacuum, almost 0 degrees, you gain this remarkable sensitivity and can test whether the fine structure constant has this varying character and has these effects on masses. Okay, well, I think that's really all there's time to do. There are many other constants you could think about varying. At big G, for example, all sorts of interesting observable effects of varying gravity. But I hope I've given you some flavour for the importance of the constants of nature, why physicists take them seriously, why they're such a challenge to fundamental theories. You know, why do they take the numerical values they do? How many of them are there? And if someone comes up next week with a solution of M theory and string theory that solves all problems, one of the first questions people will ask is, what constants of nature can you explain, if any? And lastly, this area of great current interest, some of us have been involved in, looking at the time variation of the constants of nature. Are the constants really constant? There's evidence for small variations now in other constants, like the ratio of the electron to the proton mass, again looking at quasar spectra. So astronomical observations give you the most sensitive way of probing the constants of nature, because they allow you to see the world as it was 10 to 13 billion years ago and compare it with the way it is today, and understand, ask the question, what is different about the world in the past to what it is today? Are the laws of nature the same, or are they different? Thank you.